Okay, so welcome to this video. In this video what we're going to discuss is the two-pore potassium channels. Now these two-pore potassium channels, or rather two-pore-domain potassium channels to be full, are the leaky potassium channels that you have within cells. Okay, so the structure of this video then, before I actually discuss the structure of these two-pore domain potassium channels, what I want to begin with is a reminder of the motivation for these channels. Okay, so I want to begin with some physiology rather than pharmacology. I want to begin with the importance of these things within all cells, basically, for maintaining a resting membrane potential across the cell membrane. Okay, so we'll start with the motivation for them, and then we'll look at their in detail structure and the different types that we have. Okay, right, so I'm going to start off then by discussing Nernst potentials, and then we'll get to resting membrane potential. Okay, so to begin with, what I want to discuss is what it actually even means to have an electrical potential difference across a cell membrane. Okay, so to discuss that, we need to discuss what electrical potential is. So electrical potential is a concept from physics. Okay, it is a mathematical model to help us understand this reality. Okay, and this is the mathematical model. What you do is you ascribe to every point in three-dimensional space a real number. Okay, and this real number can be positive, it can be 0, or it can be negative. Okay, but the important thing is that you ascribe a real number to every point in three-dimensional space, and this real number is going to be the electrical potential at that point. Okay, so let me just draw a little three-dimensional graph here. So here's a three-dimensional graph, and every point in three-dimensional space is going to be given an electrical potential, which is this real number. Okay, and the units of electrical potential are volts. Okay, so every point has got a certain number ascribed to it, and that's the volts of the electrical potential, basically. Okay, so now let's go to the cell then. Okay, so let's have a cell here. Basically, all the points inside the cell, at least to a decent approximation, are going to be in electrical equilibrium with one another. Okay, so they're all going to have the same electrical potential. So, if I was to get a little man, okay, so we'll have our little man here, and he had a clever machine which was capable of measuring electrical potential, he could go and stand in any position within the cell, and he would get a number, basically, the same number everywhere. Okay, so we'll call this the electrical potential intracellularly. So wherever you go within the cell, you have the same electrical potential at all of those positions, and then we'll call that the electrical potential, capital E for electrical potential, and then we'll subscript it I for intracellularly. Okay. Also, the extracellular fluid is also in electrical equilibrium, basically. All the points of the extracellular fluid will also have the same electrical potential. So if the little man was to wander around in the extracellular fluid, again, the number on his screen would not change. Okay? So, we'll call that capital E for electrical potential, and then we'll subscript it also with an E to mean extracellular. Now, these two numbers are not necessarily the same thing, okay? The membrane separates these two compartments, which means that they don't need to be in electrical equilibrium, okay? So there is potentially an electrical potential difference across this cell membrane, which just means a difference in the electrical potentials of the extracellular fluid versus the intracellular fluid. Okay, so electrical potential difference is also called voltage. Okay, so when you have an electrical potential difference across the cell membrane, you can also call that a voltage across the cell membrane, and it's given this symbol V. Okay, now strictly speaking, when people talk about electrical potential differences or voltages across the cell membrane, they should tell you exactly which direction they mean in. They should say from extracellular to intracellular. Strictly speaking, people should say this. They should say the electrical potential difference across the cell membrane from extracellular to intracellular, or the voltage across the cell membrane from extracellular to intracellular. Okay, so in full I will denote it like this: the V for voltage from extracellular to intracellular across the cell membrane, basically. So, what does this mean? Well, this will mean if this little man stood in the extracellular fluid and used his machine, he would get a certain number on that screen, okay? And the number he would get is the extracellular electrical potential, this number here, okay? If he was to then cross the membrane and go into the intracellular fluid, the number on his screen would change. And it would change to this value here, the electrical potential of the intracellular fluid. Okay, the voltage from extracellular to intracellular across the cell membrane means how much would the number on his screen change if he moved from extracellular to intracellular. So how much does the number on the little man's machine change if he moves from extracellular to intracellular? That is what is meant by the electrical potential difference across the cell membrane from extracellular to intracellular. So let's write this out in terms of the electrical potential extracellularly and also the electrical potential intracellularly. Okay, so we want how much the number on his machine would change if he moved from here to here. Well, that's going to be the end number, the end result, which is the electrical potential intracellularly. So after he's moved, the number on his screen will be the electrical potential intracellularly. Subtract off the original number, which was the electrical potential extracellularly. Okay, so this is the answer to what the electrical potential difference across the cell membrane is in terms of the extracellular electrical potential and the intracellular electrical potential. Now, this is going to usually be kept at negative 65 millivolts, and we want to understand how do you manage to keep it at negative 65 millivolts. But first, let's just discuss what that actually means. That means that the electrical potential intracellularly is lower than the electrical potential extracellularly, and it's lower by 65 millivolts because if the little man moves from extracellular to intracellular, the change in electrical potential that he undergoes is negative 65 millivolts. A millivolt just means 1,000th of a volt. Okay, so don't worry about what that means. You should also note, of course, that the units of electrical potential difference are the same as the units of electrical potential, and that makes sense because all we're doing is taking one electrical potential away from another electrical potential, and therefore, of course, it's going to remain in the same units. Okay, so if you move from here to here, the number is going to go down, and it's going to go down by 65 millivolts, is what that is telling us. Okay, so we want to now understand how do you usually maintain this electrical potential difference across the cell membrane, basically. Okay, so we're going to start off with a simpler scenario than what the true scenario is. And we're going to study first the Nernst potentials. Okay, so let's start with Nernst potentials then. So, for this we need to understand that there is a concentration gradient of ions across the cell membrane, basically. Okay, so sodium ions extracellularly, which are dissolved within the water, have a concentration of around 145 millimolar. Okay? Meanwhile, intracellularly, they have a concentration of around 12 millimolar. Meanwhile, for potassium, the concentration intracellularly is around 155 millimolar, whilst the concentration extracellularly is around 4 millimolar. Now, you might be asking, well, what does this mean? Sodium and potassium ions on their own. Why are they on their own? Well, initially, when they were dissolved in the water, they will have had a counterion with them. Okay, and this is very important to understand. Basically, when they were initially dissolved in the water, they will have been in ionic compounds, mainly sodium chloride and potassium chloride. Okay? So here is sodium and potassium chloride. Okay, but when you dissolve them in the water, what happens is these two ions get separated, and instead both of them end up surrounded by water molecules. Now, no one ever talks about the chloride anions, and the reason is that the chloride anions aren't really going to be involved in all of this, because they can't cross the membrane nearly as easily as sodium and potassium can cross the membrane. Okay, that's why we focus on the sodium ions and the potassium ions, because the chloride anions are just going to be trapped on either side of the membrane, basically. So they're not very interesting. We're interested in the sodium and potassium ions because they are actually going to be able to move across the membrane. But it is important to understand that these ions aren't just in the solution on their own, because that would mean that the solution had a very much so positive charge, which just isn't stable at all. So they are with chloride anions also dissolved in the water, which means that the water is neutral. Okay, right. So we'll start off with the simple scenario whereby the membrane has absolutely no channels to sodium within it, and only has channels to potassium within it. Okay, so we're going to assume there's no permeability to sodium, and therefore we can ignore the fact that there is a sodium concentration gradient across the cell membrane, because it doesn't matter. The sodium ions cannot cross the cell membrane, so they're as worthless to us as the chloride anions, which are stuck. Okay, that's not physiological, of course. We will come to a better model in a moment, but for now, let's just say that there is no permeability to sodium ions. However, if I draw another little picture here, there is a permeability to potassium ions. So we're going to put potassium ion channels in the cell membrane. Okay, and these potassium ion channels are going to be permanently open. Okay, so they're not voltage-gated potassium channels, they're not ligand-gated ion channels, they're just channels that are always open, and these are what the two-pore domain potassium channels are. They're these potassium channels that are in the cell membrane, which are always open, and we'll come and have a better picture of their structure later, but for now it will suffice just to draw them as basically this structure with a tube down the middle, like so. Okay, so here are leaky potassium channels, and I should say that that's another name for these. The two-pore-domain potassium channels is their official name, but they're also called the leaky channels, or the leaky potassium channels, the baseline potassium channels, or the background potassium channels are other names for them. Okay, right. So we've got these leaky or two-pore domain potassium channels within the cell membrane. And what these are going to allow is they're going to allow potassium ions, but not sodium ions or chloride anions, to move through them. And therefore, potassium ions can cross the membrane, while sodium and chloride anions cannot cross the membrane. I should have said sodium cations and chloride anions cannot cross the cell membrane. I implied that sodium ions were an anion. Okay, right. So, potassium then can cross the cell membrane. Potassium is extremely high inside the cell and much lower outside the cell. Okay, so this means that the concentration gradient is going to mean that there is a net movement of potassium out, simply because the chance of a potassium ion hitting the channel from the inside and going out is much, much higher than the chance of one hitting the outside and going up. This is around a 40-fold gradient favouring the movement out. It's around 40 times more likely that a potassium ion will move out then we'll move in. Now, let's say initially we are assuming that the intracellular compartment has the same electrical potential as the extracellular compartment. So we're initially assuming these two numbers are exactly the same, and therefore that the electrical potential difference across the cell membrane from extracellular to intracellular is zilch, okay, 0. So we don't need to worry about that initially. All we've got is this concentration gradient of potassium that's important, of 155 millimolar on one side and 4 millimolar on the other side. Okay, and what's going to happen is you're going to get this net movement of potassium ions out. Now, what does this mean? Well, potassium ions carry a positive charge, so we are moving positive charge from the intracellular compartment into the extracellular compartment. Okay, right, so this is a current. So people will often call this a potassium current because all the current means is a movement of charged particles. So the potassium ions which we are moving from intracellular to extracellular, they all have a positive charge, so they are a string of positively charged particles moving out of the cell, and therefore they are a current basically. Okay, so this is our potassium current moving out of the cell. Now, this is going to result in changes to the electrical potentials in the intracellular compartment and in the extracellular compartment. When we move positive charge into the extracellular compartment, the effect that will have is raising the electrical potential extracellularly. So this number, the electrical potential extracellularly, will go up because we are moving positive charge into the extracellular fluid. Okay, so where you have positive charge, that boosts the electrical potential of that area basically. So, dumping more positive charge into the extracellular fluid will raise the electrical potential extracellularly. Meanwhile, removing positive charge from the intracellular fluid is going to reduce the electrical potential intracellularly. So this number here is going to go down because when we had the positive charge here, that was raising the electrical potential. When we remove it, that will decrease the electrical potential here. So this will fall basically. Now, what does this mean for the electrical potential difference from extracellular to intracellular? Well, this means how much do you change if you go from extracellular to intracellular? Well, originally it was 0. However, this number's now going up and this one's going down. So clearly this number is going to become negative because this one's now going to be bigger than this one. So we're going to have to step down when we move in. So this number is going to become negative basically. Okay? Right, so we're going to start getting a negative electrical potential difference across the cell membrane basically. Now, what effect is this going to have? Well, basically this is going to start opposing the movement of potassium ions out, because potassium ions are positively charged particles. Positively charged particles prefer to be where the electrical potential is lower, which at the moment is the intracellular compartment, okay? Because we've just said that now this change is negative, so just to give you a concrete number to be thinking of, let's say it's gone down now to negative 10 millivolts, okay? So we've moved a certain number of potassium ions out now, and we've reduced the electrical potential difference across the cell membrane to negative 10 millivolts. And I will often just drop the from extracellular to intracellular. Whenever anyone talks about the electrical potential difference across the cell membrane, they always, absolutely always mean from extracellular to intracellular. Okay, so this number's become negative 10 millivolts now. So that means that the intracellular compartment's electrical potential is lower than the extracellular compartment's electrical potential, and it's lower by 10 millivolts. Okay, so the potassium ions are now going to want to be in the intracellular compartment. Okay, so now there's a little bit more of a debate, basically, because the concentration gradient still favours the movement of potassium ions out, but all of the potassium ions sort of are thinking, well, actually, I prefer to be in here, really. So what's going to actually happen is that this isn't strong enough. This isn't a strong enough lure to completely stop the movement of potassium ions out yet. It will get stronger, and then it will be strong enough to stop the movement out. But at the moment, it's not strong enough to stop the movement out. So all it's going to do is reduce the net movement out. So as you make the electrical potential difference across the cell membrane more and more negative, it's going to reduce further and further the net movement of potassium ions out of the cell that occurs because of the concentration gradient. Now, you might ask, well, surely also, you're right, you might say you're right, but surely also, this is also going to happen because the concentration gradient is going to get lower because we're moving potassium ions out of the cell, and therefore the concentration here is going down and the concentration here is going up. Okay, you are correct that because we are moving we're moving the potassium ions out of the cell, we will be diminishing the concentration gradient. However, the effect is negligible. Okay, when you move potassium out of the cell membrane, what happens is very, very quickly you will build up an electrical potential difference that is not insignificant across the cell membrane, which will block the further movement of potassium ions out. We haven't got there yet, but we're going to get there. And the number of potassium ions you have to move out to actually build up an electrical potential difference across the cell membrane that's capable of blocking potassium from moving out further is titchy. Absolutely titchy. Compared to, the number of potassium ions in a mole, for instance, it's titchy. So the number you need to move out before you actually stop any more moving out is not going to affect these concentrations, basically, because these are just too big compared to the number that you've actually had to move out. So yes, if it wasn't for the fact that the electrical gradient is going to stop the concentration gradient from moving potassium ions out before it's actually moved a significant number out anyway, then yes, the concentration gradient would diminish, but basically the electrical gradient is going to win first, basically, and the number you have to move out to build up a significant electrical gradient across the cell membrane is titchy. So we don't need to worry about these concentrations changing, basically. We can view them as though they're constant. Okay, right. So, as I said, we've gone down to around negative 10 millivolts now, but this is not strong enough to completely stop potassium ions moving out. It will just weaken it slightly, so the arrows become smaller. Okay, so you will still move a net number of potassium ions out of the cell. Okay, and understand once again that the actual number that is moving is titchy compared to the number in a mole, for instance. Okay, so potassium ions continue to move out, and again this will make these electrical potentials even more extremely apart, basically, because the more potassium you move out, the more the extracellular electrical potential will go up, and the more the intracellular electrical potential will go down. So this number is just going to become more and more and more negative. Okay, so let's say it's now gone down to negative 40 millivolts. Okay, now that's better, it's getting more and more negative, it's getting stronger and stronger, but that's still not going to be enough to actually completely stop the movement of potassium ions out because of this concentration gradient. Okay, so you've still got a net movement out, basically, you still haven't reached an equilibrium. Okay, so you'll continue to move potassium ions out, which means that the electrical gradient will get stronger yet again, and it will continue on all the way down until you get to around negative 85 millivolts. Okay, and this is the electrical potential difference that you need to have across the cell membrane so that it's strong enough to completely stop potassium from moving out. So at this electrical potential difference, or thereabouts, across the cell membrane, you get no movement of potassium out, even though you have this concentration gradient across the cell membrane. Okay, this electrical potential difference across the cell membrane is known as the Nernst potential for potassium. Okay, and note that it is not a number associated with potassium, it's a number associated with these potassium concentrations that you have across the cell membrane. It's associated with this potassium gradient, basically. So when we say Nernst potential for potassium, you might like to add across a cell membrane, basically, because it's not something that's fundamental to potassium, it's something that's fundamental to the concentration gradient in potassium that you usually have across the cell membrane. Okay, so this is the electrical potential difference that you would need to have across the cell membrane to get no net movement of potassium across that cell membrane, basically. Okay, and it's often given the symbol V for electrical potential difference or voltage, and then K plus there to remind us that it's the electrical potential difference across the cell membrane at which there is no net movement of potassium across the cell membrane. Okay, right, so if you then went beyond that, if you went to something like negative 95 millivolts, okay, that would now be strong enough to actually drive potassium moving in the opposite direction. Okay, so potassium would actually move into the cell. The electrical gradient would now be stronger than the concentration gradient, and you would move potassium into the cell. So this is what is meant by Nernst potentials of ions. Okay, right, so before we just finish this part of the video, what I want to do is discuss the same thing for sodium. Okay, and this shouldn't take us long now because we know the gist. Okay, so in the case of sodium, the concentration gradient is in the opposite direction. Okay, so we've got a concentration of sodium of around 145 millimolar extracellularly, and a concentration of around 12 millimolar intracellularly. And then we've got these leaky sodium channels that are also in the membrane, which we're not going to discuss in this video. We're looking at the leaky potassium channels. Okay, so let's add a bit of colour on here because we haven't used colour once in this entire video. Okay, so here is a leaky sodium channel in orange. So, again, imagine that the electrical potential difference, imagine that the electrical potentials across the cell membrane start off at an equal value, basically. So imagine that we start off with an electrical potential difference across the cell membrane of 0. Then what will happen is sodium ions will move into the cell because of the concentration gradient, okay? And we're imagining at the moment that the cell membrane is only permeable to sodium ions, so we don't need to worry about potassium, we don't need to worry about chloride being able to move. All that's going to happen is sodium ions are going to move. This then, when we move positive charge into the intracellular compartment, is going to raise the electrical potential intracellularly, and because we're moving the positive charge out of the extracellular fluid, we will decrease the electrical potential extracellularly. Okay? This then will create an electrical potential difference across the cell membrane that is positive, because now you're going to have to step up as you go from extracellular to intracellular. So this number is going to become positive, basically. Okay, and initially it will start off low, so maybe it will go to plus 10 millivolts. Okay, and then what will happen is when the electrical potential difference starts to build up, then what will happen for the sodium ions? Well, now the sodium ions again are a positively charged ion, so they want to be where the electrical potential is lower, which now is the extracellular compartment. So the sodium ions will now feel a lure towards the extracellular compartment. Now, at plus 10 millivolts, this isn't strong enough to completely stop a net movement of sodium into the cell because of the concentration gradient, but it will reduce the number of sodium ions that are coming in. So it will reduce this current of sodium coming in. Okay? then because you've still got a net current in, you're going to raise the electrical potential intracellularly and decrease the electrical potential extracellularly even more, which means that this number will become even more positive. So it will gradually build up and up and up until it gets to plus 60 millivolts, which is the electrical potential difference that you need across the cell membrane to completely stop any sort of net movement of sodium into the cell with these concentrations extracellularly and intracellularly. And this then is called the Nernst potential for sodium, or VNA+. So it's the electrical potential difference that you need to have across the cell membrane to get no net movement of sodium across the cell membrane. Now, I should just say that Nernst potentials are also sometimes called equilibrium potentials. And the reason for that is that it's the point at which you are at an equilibrium. Because when you have no net movement of sodium into the cell, then you're going to get no further change to the electrical potentials on either side of the cell membrane. So the electrical potential difference across the cell membrane will remain exactly the same, i.e. you have reached an equilibrium basically. Okay, so that now concludes our discussion of Nernst potentials. In the next video, what we'll do is combine all of our knowledge now and all of our understanding into the real scenario, because you'll notice that the electrical potential difference across the cell membrane of negative 65 millivolts is neither of these. And the reason is that cells have both sodium channels and potassium channels, and we need to put the two together basically and get a complete picture, and that's the resting membrane potential. But we'll do that in the next video.